In continuation with the buckling analysis of plate, today we will discuss the buckling analysis of cylindrical shells. So as you know, the plate is a planar element and it may subject to bending upon the action of the forces. But in the case of cylindrical shells, there is an initial curvature already present in the shells, and the membrane action resulting from the secondary middle surface forces is therefore has to be accounted for the case of shells, and this is also required for the case of large deflection studies on plate. In this video we are going to see the generalized linear theory of cylindrical shells and the equation proposed by the Donnels. So this is the buckling of the axially compressed steel, sorry, cylindrical shells. You can see on the screen, and you can go through the introduction part. Coming to the linear theory of cylindrical shells, there are some assumptions involved. The thickness of the shell is very small compared to the other dimensions of the shell, and therefore the cylindrical shell is thin. The large deflections are compared to the thickness of the shell. Also, the material from which the shell is constructed is homogeneous, isotropic, and it should obey the Hooke's law. Then the lines normal to the metal surface before bending remain straight and normal during the bending. The shell is initially a perfect cylinder and it is loaded concentrically at every cross section. So you can see here the part of the cylindrical shell is that in the vertical axis y perpendicular to the screen, and the Z is in line with the screen, and R is the radius of curvature, and the deformation in the x direction is called termed as U. Deformation in the y direction is termed as B, and the plate is having shell is having a thickness of H. Similarly, the figure beyond C shows the in-plane forces, and the C shows the out of plane or transverse bending moment and the shear forces. You can see the axial forces and shear forces in the figure B, and the moments and shear forces in the figure C. So considering the equilibrium, so the derivation for the linear theory for shells are proposed by various researchers, and although the shell is a very complex to analyze and to derive the equations, several researchers has made the equations based on so many assumptions. So the final equation will depend on the extent of assumption. The Donnel also proposed an equation which is taken from the plate equations and modified for the shells, and the results are seem to be very nearly accurate with the real condition. So we are taking the Donnel's equation, the linear theory, for the analysis of the cylindrical shells. So most of the equations which we'll discuss here will be from the from the theory portion of the plates. So when you write the equilibrium equations considering the in-plane forces. You have dou nx by dou x plus dou nxy by dou y equal to 0, and dou ny by dou y plus dou nyx by dou x is equal to 0. And these are the equilibrium equations in the x and y directions for shell are identical. Those obtained in the equation of the plate in the previous chapter, and that is just reproduced here. Now our focus is on finding the equilibrium in the z direction. As shell is having a curvature, there are little bit complexity involved, and it's necessary to take the curvature of the element into account, both the initial curvature and the curvature due to the bending is concerned. So we're discussing that the initial curvature is a sole property of the shell, while the curvature due to bending can occur even in the case of plate. Due to the initial curvature of the shell, the NY forces as indicated in 7.2 have the component. So the NY force is in the direction of uh, yeah, like perpendicular to the screen, and they have the component in the z direction. We have ny here, dy element, dy by r is angle, and the direction is equal to ny into 1 by r dx dy will be the component of the ny forces in the z direction. Similarly, the Z components of the in-plane forces of the cylindrical shell obtained by adding the terms given in 6.3 to the term 7.3. 7.3 is our uh, component in this direction. We have derived the in-plane conditions for the plate. So those clubbed together to give the equation 7.4. To the Z components of the in-plane forces must be added with the transverse shear force also as given in dou qs by dou x plus dou qz by dou y into dx dy. So the outer plane or transverse forces includes the moment as well as the shear forces also. Those are described in equation 7.6. Since the equations of moment equilibrium about the x and y axis do not change in going from the plate of the shell element plate to the shell element. Equation 6.6 and 6.7, which were derived for the plate equation, is valid for the shells also, and it is rewritten as here. And now we can combine the equation 7.4 by the in-plane forces and the equation 7.6 due to the out-of-plane forces. I want to obtain the equation of equilibrium in its direction as a long equation dou square mx by dou x square minus dou square mxy by dou x dou y plus dou square mz by dou y square plus nx into dou square w by dou x square plus 2 nxy into dou square w by dou x dou y plus ny into 1 by r in plus dou square w by dou y square equal to 0. Now we have the force deformation relations, and like we did for the plate, the displacements and strains are separated into the middle surface and the bending terms. Thus we have uh, the displacement total is equal to due to the um, initial like the planar deformation plus due to bending, all are taken like that, and the epsilon, the strain in s direction as well as strain in y direction as well as the shear strain is also taken as the addition of two different deflection effects. So then we have the moment curvature relationship which we had derived for the plate equation, and those is also applicable for this the shells. And after that, so this is the mx equation, my equation, and mxy equation which we derived from the plate. Next is middle surface force deformation relationship, and we have derived the relation between the axial forces and the axial stresses in the plate equation as given for 7.15, 7.16, 7.17, and similarly applying the equation, the 7.11, the displacement relation 1 2 and 1 3 into the these relations will give you the modified equations of 7.19, 7.19 and 7.20. And we have, yeah, so after this once we substitute the appropriate derivatives of 7.8 through 7.10, so we have those equations here, the derived equation for the moments from the plate equation, and 7.24 to 7.26, which is the relation between the axial forces and the axial stresses uh, taken from the displacement equations into equation 7.1, 7.2 and 7.7, which were the initial equation for the displacement relation, like the dou and x, like the axial forces for the z direction, 7.12 and 7.2. And 7.7, that equation is on the, yeah, that's the final equation which includes the in-plane forces and plus the transverse forces. So those will provide you the lengther equation, and this equation, after considering the higher order terms and the neglecting the uh, lower values, we will simplify it to get the final equation as d into delta raised to 4w minus delta raised to 4 into px into dou square w by dou x square plus py into dou square w by dou y square plus 2xy into dou square w by dou x dou y plus eh by r square into dou raised to 4w by dou x raised to 4. So this equation, you can read through the uh, like the assumptions taken for neglecting the higher order terms, and the linear 8th order equation in W is known as the Donnel equation, and by letting Py is equal to SSY 0, it can be used to obtain the critical load of a cylinder subjected to axial compression. That is, Pxy is neglected. The Px is the axial compression. Similarly, by letting the SSY equal to the applied shear force, or by letting Py equal to the hoop force, cause the pressure, one can use the equation to obtain the critical load for cylinder subjected to the torsion or external pressure. So it's basically, this will be the main sub equation for analyzing the cylindrical shells for any type of loading, and the necessary conditions can be applied into the equation to get for the action of steel shells, sorry, cylindrical shells for axial compression, the external pressure as well as torsion conditions. Thank you.